Hello class. So this is the first video on section 5.4. This is going to be the last section we're going to be covering for this class. As I mentioned, we're going to be skipping section 6.1. Right? So this is the last section, section 5.4. This section is actually not that bad. There's really not much new. Basically what we're going to see is in the first part, we're going to see some shortcuts for evaluating definite integrals. And then the next part is going to be defining what the average value of a function is. In terms of new material, it's not going to be anything really new. So it should be an easy section to go through. So yeah, let's just go jump into it. So first, let's make some definitions. I might have asked you about this in previous homeworks, maybe in homework 1 or in other homeworks. But if not, we can just see the definition real quick. Okay, so we're going to define what even and odd functions are. So first, starting with an even function. So an even function is a function that satisfies that when you plug in negative x into the function and you simplify it, you get the original function back. So that's an algebraic definition. Right? Given any function that we have, stated exactly or clear, given any function we have, we can plug in negative x, simplify, and see if we get f of x. So that's an algebraic definition. Here I'm giving you a graphic definition. If you actually draw the graph, it should be symmetric about the y-axis. Okay? So what are examples? X to the n, whenever n is even, and cosine and secant. Right? So I give these examples. These are the ones we're going to use the most. I don't think we're use secant too much, but for sure x to the n and cosine. So here what I did is I graphed some things. So I graphed x squared, right, which it's x to the n where n is even. So again, that's an even function. And I also graphed cosine. You can see graphically what's going on. If you draw this line about the y-axis, just covering the y-axis, you can see that the graph looks the same to the right and to the left of the y-axis, right? Meaning that it's symmetric about this y-axis. Right? So graphically, you can think of it like that. Another way you can think of it is the y-axis is the middle of your book. If you close the book, then whatever's to the left and to the right of that axis overlaps. You can see that that's what's going on here. So again, graphically, just look at the y-axis. If whatever's to the left is equal to whatever's to the right, then that's a symmetry about the y-axis, meaning your function is even. Of course, there was also the algebraic definition, which was, and let me give you an example. So let's say f of x equals x squared. To verify the algebraic definition, we want to plug in negative x into our function. So if we plug in negative x, we get negative x squared. We have two negatives, so those cancel. We get x squared, which of course is the original function. And this was the algebraic condition for even functions. If you plug in negative x and you simplify, you should get the original function back. So that's what an even function is. You can verify it either algebraically or by graphing it. Now, the other type of function we have is an odd function. And as well as before, we have an algebraic definition and a graph definition. So what's the algebraic definition? Again, it's about plugging negative x into your function and simplify it and seeing what you get. So if you plug in negative x into your function, and what you get out after simplifying is the negative of the original function, then your function is odd. Graphically, this means symmetry about the origin. That's a little bit harder to explain. So as you saw on the previous slide, I also drew examples for this. So I'll show you what that looks like. So what are examples of odd functions? Well, x to the n for n odd is an odd function. And then all other trig functions, right? So it turns out that cosine and secant are the only even functions. All other trig functions are odd. So again, we see examples. So here I graphed two odd functions. X is odd because it's x to the 1, so the exponent is odd. And then sine of x is odd because it's not cosine or secant. So how can you identify graphically a symmetry about the origin? So that was the condition for odd functions. It was symmetric about the origin. So basically what you want to check is you have these quartiles. Remember from algebra, you studied that this quartile here is quartile 1. We have quartile 2, quartile 3, and quartile 4. So what do you want to look for? Well, if your graph is the same or or think of reflected. So if whatever's in quartile 1 is reflected in quartile 3, and whatever's in quartile 2 is reflected in quartile 4, then you have a function that has odd symmetry about the origin. Sorry. So here you can see that whatever's in quartile 1 is reflected into quartile 3. Now in quartile 2 and quartile 4, we don't have anything, so nothing is reflected, right? But that's the idea. That's how you would identify something that's an odd function. See that whatever's in quartile 1 is reflected into quartile 3, whatever's in quartile 2 is reflected into quartile 4. So that's x. And then for sine, you can see that the same thing is going on. Here we have, change the color. Here we have quartile 1. And you see that whatever's in quartile 1 is reflected onto quartile 4. And then, of course, whatever's in quartile 2, which is nothing, is reflected onto quartile 3, not quartile 4. And then whatever's in quartile 2, which is nothing, is reflected into quartile 4. So that's the idea. You're basically changing the quartiles. So the odd quartiles, you're reflecting those, and the even quartiles, you're reflecting those. So that's how you can find it graphically. Unfortunately, it's not as simple as, oh, it's symmetric about the y-axis, but still, you can identify it. And then, of course, we can also identify this algebraically. Let's do, for example, the x function. So if f of x equals x, let's see what happens if we plug in negative x. So plugging negative x, let's use negative x, which of course is the negative of the original function. And that was the condition for an odd function. If you plug in negative x, you get the negative of the original function. So again, for both even and odd functions, you have this graphic definition and you have this algebraic definition, and you can use either. So why are we going through this? Well, the reason why is because we can simplify our definite integrals if we had even and odd functions. For example, here's what the theorem says. Let A be, use quotations, let A be a positive real number, and let f be integrable, which, remember, integrable for us is the same as continuous, on the interval negative a to a. So what do we conclude? If f is even, then the integral of f of the interval negative a to a is just twice of the integral of f on the interval 0 to a. Then if f is odd, then you're finding the definite integral from negative a to a of f, well, that's just 0. So why is this happening? Well, it's really easy to check graphically, right? So let's see what happens when f is even. So again, let's just graph x squared. So we have the interval negative a to a here. So a could be any number. Let's say it just has to be positive, so greater than 0. So say we're doing negative 2 through 2. So a equals 2. We see what the graph looks like. So it's going to look something like this. And of course, it's symmetric about the y-axis, right? So it looks the same on both sides. Now, see what's happening with the net area. Because remember, a definite integral is calculating net area bounded by the function and the x-axis. So if you notice, the area to the left of the y-axis is the same as the area to the right of the y-axis. Meaning that if we want to find the whole area, if we want to find the integral from negative 2 to 2, so this was the graph x squared dx. Well, you can see graphically that, well, it's just twice of the area bounded on the interval 0 to 2. So instead of finding the area to the left and to the right, you just find the area to the right of the y-axis and multiply by 2. Why? Because both areas are the same. And that's the idea. And again, this works because it's an even function. It's symmetric about the y-axis. Now what's going on with odd functions? So now let's plot y equals x. That's an odd function. And again, let's say we're going from, let's say, maybe negative 3 to 3. Actually, let's say we're going from negative 3 to 3. And again, we're looking at the net area bounded by the function, the x-axis. So here we have this area here. And then to the right of the origin, we have this area here. Now, if you notice, the area to the left is the negative of the area to the right. Why? Because the areas are the same, but the part in blue is below the x-axis, so you count it as negative. So if we were trying to find what this net area is, which is the same as finding the integral from -3 to 3 of x dx, what would we do? Well, by definition, we would take the negative of the area below the x-axis and add it to the area above. But those are equal, so they cancel out. So this just becomes 0. And that's the whole idea. Why does this happen? Well, because we have an odd function. So whenever you have an even function and you're taking an integral on a symmetric interval, so something that looks like -a to a, you get twice as the integral from 0 to a. If you have an odd function, and again you're integrating over a symmetric interval, so something that looks like -a to a, you just get 0. And that's the shortcut. For even and odd functions, we have this really nice shortcut that simplifies the work. So that's the whole setup. In the next video, we'll just see an example of this. All right, so here I showed you one. We're going to do one that's not as obvious.